Welcome back to the workshop. We want to continue taking a look at section 3.4, which is probability density functions. Yes, excellent. So we have one more definition, much like when we considered the discrete random variables. We said here is a probability distribution, and then we can add up the probabilities so that way we end up with a cumulative probability distribution. And that's exactly what we want to take a look at here in the continuous version. And it actually has exactly the same name. So whether we're talking about discrete or continuous random variables, when we look at the probability of the minimum value all the way up to the one of consideration, we have the distribution function or the cumulative distribution function. Right, same name, that pair of names is acceptable for the discrete and the continuous case. So let's take a look at our notes. If x is a continuous random variable and the value of its probability density at t is f of t, so instead of saying x and f of x, we're saying t and f of t, the function given by, right, the cumulative, what's the probability from negative infinity all the way up to some particular value of interest? Well, that would be the right probability from negative infinity all the way up to x. This is the cumulative probability distribution function. So the integral should be from negative infinity all the way up to x. And this is why we need t, because I can't talk about integrating with respect to x and have x as one of the integration bounds. That's not acceptable. So we need to have a different variable here in the integral. So f of t dt. And in this case, we want this for x values that are between negative infinity and positive infinity. Excellent. So this little bit here, this is really just a side note. It's not part of that definition. The cumulative probability is the probability from all the way at the bottom all the way to what we're interested in, this particular value. And that, by the definition of the probability density function, is simply this. But since we're looking at this specific scenario, it's called the distribution function or the cumulative distribution function. Awesome. So let's find the cumulative distribution function for what we showed in the previous example. Could serve as a probability distribution function, right? Here's the example we just did. Can it serve as a probability density function? Yes, it can. So let's find the cumulative distribution function for this particular distribution function, or sorry, for this particular density function. All right, okay, so we're good there. All that we have to do is, right, f of x is the integral from negative infinity to x of f of t dt. We already calculated this integral once, so it's nothing too crazy. All right, it's the integral from negative infinity to x. There's only one integration bound that's not good now instead of two. So this is 1 over pi times x squared plus 1 dx. We already know that this is 1 over pi, and we only need one limit here because this is the only integration bound that's infinite. So we have limit as a goes to negative infinity of the integral of this, I pulled the 1 over pi out, is arctangent of, oh, and actually here I said that we didn't want this to be x. I wanted it to be t, hence t and t. There we go, that looks better. Yep. So arctangent of t evaluated from a to x. Excellent. So this is 1 over pi times the arctangent of x minus the arctangent of a, but it's the limit here, so minus the limit as a goes to negative infinity of the arctangent of a. Excellent. 1 over pi times the arctangent of x minus, we already said that this was negative pi over 2 So I can call this 1 over pi times the arctangent of x plus, right, minus gives us plus 1 over pi times pi over 2 is 1/2. And that's it. That's our cumulative distribution function. And that's all that we wanted to show for now. So we've got one more video on continuous random variables, or probability density functions rather. And we'll look at that in our next, or we'll look at the theorem in our next video. That's all that we have left. So I'll see you guys back in the workshop in just a minute.